Welcome to an example on how to solve a system of two linear equations with two unknowns using Cramer's rule. Cramer's rule is a method for solving a system of equations that uses determinants. So the first step in using Cramer's rule is to make sure the linear equations are in standard form, or this form here. If the linear equations are in this form, then the solution, or the value of x and y that satisfy both linear equations, is given by the quotient of these 2 by 2 determinants. Notice that a sub 1 and a sub 2 are the coefficients of x, b sub 1 and b sub 2 are the coefficients of y, and c sub 1 and c sub 2 are the constants. So if we take a look at these 2 by 2 determinants, let's first focus on the denominator of both x and y. Notice both 2 by 2 determinants contain the same elements, where the first column contains the coefficients of x, and the second column contains the coefficients of y. And then for the numerator of x, if we compare the 2 by 2 determinant in the numerator with that in the denominator, notice for x the second column stays the same, but the first column, which in the denominator contains the coefficients of x, is replaced with the constants. So when solving for x, in the numerator we replace the coefficients of x with the constants. Now looking at the numerator for y and comparing it to the denominator, notice how the x coefficients, or the first column, stays the same, but the second column, which in the denominator contains the coefficients of y, is replaced with the constants. So let's go ahead and apply this to solve the given system. And we'll start by writing in the elements for the denominators for both x and y. So again, using our formula, the first column will contain the coefficients of x, which would be positive 2 and positive 1, again for both x and y. And then the second column will contain the coefficients of y, which would be negative 3 and positive 2. And now for the 2 by 2 determinant for x, if we compare it to the determinant in the denominator, the second column is going to stay the same. And then because we're solving for x, we're going to replace the x coefficients with our constants, which would be 16 and positive 1. And then for the 2 by 2 determinant in the numerator for y, the first column will stay the same, but the second column that contains the coefficients of y will be replaced with the constants, so we'll have 16 and 1. Now we'll evaluate these determinants, simplify, and we'll have our solution. To find the value of our 2 by 2 determinants, we'll find the difference of the product of the diagonals. And let's go ahead and start with our denominators. Here we'll have 2 times 2 minus negative 3 times 1. Well, that would be 4 minus negative 3. Remember, this 2 by 2 determinant is the same as the denominator for y, so we'll also have 4 minus negative 3. The numerator for x, we would have 16 times 2 minus negative 3 times 1. And then for the numerator for y, we would have 2 times 1 minus 16 times 1. Well, that would be 2 minus 16. So we would have x equals, this would be 35 divided by positive 7, which is equal to 5. And for y, we would have 2 minus 16, that's negative 14, divided by positive 7, which is equal to negative 2. So we can see our system has one solution, where the x value is positive 5 and the y value is negative 2. And because our system has one solution, we can say the system of equations is consistent and independent. Let's go and take a moment and check our solution by subbing the value of x and y into both linear equations. So looking at the first equation, we would have 2 times x, which is 5, minus 3 times y, which is negative 2, equals 16. Well, we'd have 10 minus 3 times negative 2 would be plus 6, which is equal to 16, so that checks. Let's also check the solution in the second equation. X plus 2y equals 1, so we would have 5 plus 2 times negative 2 equals 1. We'd have 5 plus negative 4 equals 1, which is also true. Okay, I hope you found this example helpful. Next, we'll take a look at solving a system of three equations with three unknowns using Cramer's rule.